Hello, this is Mrs. Hilt with your Unit 1 review. We're going to go over concepts that you may be assessed on with the Unit 1 assessment that is tomorrow, as well as do some practice problems. All right, first thing, the quantity of 17.2 kilometers per hour west is an example of, and go ahead and choose your answer. All right, the correct answer was velocity. Now I'm going to continue that question, and I want you guys to identify what you would do if we needed to change this into an acceleration. And I don't mean applying any actual math, but if you just needed to fix that number, like something about the units or direction to make it an acceleration, speed, and displacement, I want you to do that and write those down. So pause the video and go ahead. All right, what those would look like for acceleration. Everything would be the same except you need to have the time or the denominator squared. For speed, the initial number in units, those would be all the same, but west would be taken off because speed is just a magnitude where velocity is a magnitude as well as a direction. For displacement, we would just have kilometers. We do need to have the direction, but no time because displacement is some type of distance unit, and the west makes it displacement instead of just a distance. All right, here is a vector mapping practice problem. So Christy and Jeff decided to try out a new quarantine activity that they could do outside, slackline. Below is an image to represent the slackline hung in the park. Christy started out on the slackline, clinging to the tree on the left. So this one right here, and I made a little purple dot. She walked 5 feet towards the center of the slackline. Then the line sagged down 2 feet. Miraculously, Christy walked 4 more feet away from the tree she started at before falling to the ground. I want you guys to not only draw the vector map, but determine what Christy's distance and displacement is. The box scale is 1 foot. Okay. And for the part where she is walking 5 feet toward the center of the slack line, in reality, that would be sagging downward. Just have her go, or me, go directly left at that point, or sorry, directly right at that point, and then do the 2 feet down. Go ahead and pause the video. Okay, let's see how you guys did or check your work. And I will zoom in on the bottom part. So Christy walking 5 feet over, that is shown right here. Make sure that you do have the arrowheads at the end of your vectors so it points in the direction that it is moving. Then she goes 2 feet downward when the slack line sagged. Somehow I was able to move 4 feet over still when the line was sagging. Then I plummeted to the ground where I'm surprised I didn't fall way back there. So here's my vectors. And for calculating the displacement, because we are moving in different directions here, we have to use triangles in the Pythagorean theorem to determine what our displacement would be, or what my displacement would be. So drawing that displacement line, you have to start from where you started and draw it directly to the very end. So everything in between you really can ignore. You just care about the starting position, the ending position, and then you'll use the grid to figure out what the lengths of each side of the triangle are. So it's really important if you guys are asked to make a problem like this or do something like that, that you identify the size of the box. If we don't know how long or how large the boxes are, we won't be able to identify the sides of our triangle. Now I'll scooch over to my calculations. So here's my distance calculation, just adding up all of the different distances that I traveled. Comes up to 12 feet. For the displacement, this was one side of the triangle, this was another side of the triangle. The C is the hypotenuse. So you need to square those individually. And to get C all by itself, you need to square root both sides. So my displacement, that is unrounded, not to the correct sig figs, is a little over 9 or a little under 9.5 feet. All right, some dimensional analysis problems, or a dimensional analysis problem. Mullen decided to have a donut party. Enough donuts were purchased to allow 900 people to have 2 donuts each. If each box of donuts contains a dozen, how many boxes were ordered? Pause the video and try out this calculation. All right, so our starting value is going to be the 900 people, and the conversion factors are ones that we have to make up based on what the problem told us. So if we have 900 people and each of them are getting 2 donuts per one person, it means we do need to multiply 900 by 2. And to figure out how many total boxes to order, once we have the total number of donuts, we divide it by the number of donuts per one box. So we would need to order, or the school would have to buy 150 boxes of donuts to feed 900 people if they're getting 2 donuts apiece. All right, so the next section is all about reading distance versus time graphs and then velocity versus time graphs. I found this online. I really liked how it described what is going on at different portions of each of these graphs. And these graphs are actually the same movement. Okay, so they're different graphs. We have distance versus time and velocity versus time, but this is the same object that is moving, and it's just represented in the two different graphs. So we have down here a positive acceleration, positive slope, and in a distance versus time graph, that's the more exponential or the swoopy kind, as I know I've said in office hours a couple times. Okay, so those are all the comparisons between those two. Pause the video if you wanted to check those out a little further. We're going to move on to some practice problems. Problem number 1, and for all of these, pay close attention to the units. So this is a distance versus time graph. And I want you guys to identify what the object is doing between 32 and 36 seconds. So 32 to 36. Okay, I hope you guys picked option C. The object is standing still or it is not moving. So I drew straight lines up at 32 and 36. I drew one line and I was able to copy and paste it, and that truly showed me that they are at the exact same point. Since this is a distance versus time graph, that means that their distance did not change, therefore they are standing still. Next question. During which time period is the object moving the fastest? All right, to figure out when the object is moving the fastest, we need to look at where on the graph has the steepest slope. So in the light brown or tan color, I have the slopes of the three different, or A, B, and C. And in the green is the slope for D, which is the correct answer. The object would be moving the fastest at that point because the slope is the greatest. And remember what the calculation is for slope is the y over x, so meters per second. Therefore, greatest slope, greatest velocity at that point. Next one, which of the following is not an example of acceleration? Okay, the thing you need to pay attention to is the units. So don't let this double denominator confuse you. What that is just saying, it is that it is saying some velocity divided by time, again, some velocity divided by time, and this is the same thing. This would just, this meters per second squared for D. It could also be expressed how C's units are. This one is just more condensed. So because C does not have a squared time in the denominator, it is not an acceleration, it is actually a speed. What does the slope, distance, or displacement over time of a position versus time graph tell you? Okay, so position versus time, distance or displacement over time, what does that tell you? Right, these graphs tell you the velocity. I have an example drawn to the right here. If it was a flat or horizontal line, it would be a zero velocity. If it were a linear line like this, be constant. And if it was exponential, changing velocity, which is the same thing as something accelerating. But no matter what, the slope of the line is telling you the velocity. Okay. This one is just a changing velocity. All right, so this is another position versus time graph. It does not say it on the axes, but the question does tell you. I want you guys to describe the motion of this graph. And if you want to get creative with it, like come up with a little story, go right ahead and pause the video to describe the motion. All right, so I highlighted on the different colors here what the graph is actually telling you, and then I came up with a little story on the right of something that could have been happening that tracked this. So maybe Jeff drives to Costco along line segment A. This is the point where he's parked and now he is shopping at Costco, so his car is not moving along line segment B. Then he, after he's done, starts driving toward home a little bit faster. And the reason why I said faster this time is because this is a steeper slope than what it was for A. So he's driving faster, but then he passes home and decides to go further past home to go get ice cream for Christy. And unfortunately, this graph does not have him coming back home to deliver the ice cream to Christy. Okay, so if you ever see these positive and negative regions, if it's a distance or position versus time graph, it's not about having like a negative velocity, or you do have a negative velocity, but you need to think of it as moving in the backwards direction. So I always like to think of this middle line as home, or like home base. So traveled away from home, wasn't moving, traveled back toward home, but then went past their house in the opposite direction that they were originally going when they started off. All right, for this, you guys are going to answer both of these questions, and they'll be popping up very shortly. Okay, let's see how you did. So everything is highlighted and color-coded. During the intervals, he was traveling in the positive direction. Anything that has a positive slope means that he was traveling in the positive direction. It's okay that this one is in the negative region of the graph because they are going towards the positive area, or because the slope is positive, they're moving in the positive direction. When they're traveling in the negative direction, it is this one, and it has a negative slope. Next up, during which interval, oh, sorry, you know what, the questions will pop up on the side. Go ahead and answer these questions. See how you did. During which interval was he resting in a negative location? So the location must be negative and he must be at rest. Therefore, it is the flat line right at the beginning. And during which interval was he resting in positive location? Flat line, therefore no movement, also in the positive region. Next, try this one out. All right, so this one you did need to do some calculations, or if you compared the slope, that's fine too, just based on how the lines look. But I showed the calculations down here when he was traveling at the same speed. Even though this one is negative, his speed is the same. He's just moving in the backwards direction. Okay, so the speed is the same. Where they are moving, or where this object is moving, is in different directions. All right, some more calculations. Go ahead and pause the video and try these ones out. Okay, here is the calculations that go with each of these. So what was his average speed the first 5 seconds? So average speed, you need to have the distance that was traveled. No distance was traveled along this first line segment. 2 meters was traveled along the second line segment. So the total distance that was traveled from the start to 5 seconds was only 2 meters. For the last 5 seconds, from here to here, the object was not moving and then went 3 meters in just 1 second, not moving again, and then traveled another 3 meters. And oh, sorry, I was thinking that I was going from 5 to 10. We are going from 6 to 11, so still 3 meters at rest, another 3 meters, and then another 3 meters when we're in the negative portion of the graph. So a total of 9 meters traveled for the distance and 5 seconds. All right, some more calculations. Go ahead and pause your video and try these ones out. Here's all the work that goes with each of these. So the average velocity for the first 8 seconds. I drew a line right here to show start, and then 8 seconds. So what's the big difference between velocity and speed is that speed is the total distance, velocity is the displacement. So the difference from the initial to the final position. So our initial was -2 meters. Our final for the first 8 seconds was 3. And finding the difference of those, because 2 is negative, is 5 meters. For the 6 to 10 seconds, and did I do this wrong? Yes, all right, I apologize. My work down here is incorrect. Please ignore that. For calculating this one out, you want to go from 6 seconds. You know, why don't I change this to red? No, it's too close. Blue. 6 seconds to 10 seconds. There was actually no distance traveled, 0 meters here. And if we want to set up the whole calculation, 0 meters initial and final. The time was a total of 4 seconds. Either way, 0 meters per second. So please ignore what is down there. I was going from 6 to 8 seconds instead. Okay, another calculation. What is the total distance that was traveled? And what is the average speed for the entire 11 seconds? Go ahead, pause the video, and try these ones out. Okay, for calculating the total distance, you don't need to add anything for any of the horizontal lines because there is no movement or no changing of positions. A was 2 meters, B 3, and the line segment C was 6 for a total of 11 meters traveled. And then the average speed, since we have the total distance already traveled calculated, that is our numerator. Total time is 11 seconds, so the average speed was 1 meter per second. Okay, now we are going to try out net displacement and average velocity. Go ahead, pause the video, and try these ones out. Okay, here's all the work for the displacement. Again, it's final position minus the initial position. Here's our initial, here's our final. So we really only went down 1 meter. So we can think of that as negative 1 meters or 1 meter in the backwards direction. And then for the velocity, we've already calculated what our displacement is, which would be our numerator, and then the time is 11 seconds. Simplify that fraction to get negative 0.09 meters per second. And make sure that you do always simplify this so that your denominator is 1. All right, new graph for this one. All of the questions should be answered based off of what is over here. Go ahead and pause. Sorry. Go ahead and pause the video and try these ones out. All right, so first one, when interpreting a position versus time graph, how do you know which direction the object is moving? So it's all based on the slope of the line. If the slope is positive, it's moving in the forward direction. If the slope is negative, moving in the backwards direction. When does the object turn around? It is whenever the slope changes. So going from a positive to a negative. So I chose at 2 seconds. They did a complete turnaround, and then between 7 and 8, they were going in the backwards direction, stopped, and then started going back in the forwards direction. And for the intervals that a person is moving forward, backward, or not at all, go ahead, check out your answers there. So it all should depend on if the slope is negative for backward, positive for forward, and 0 for not moving. And to sum it up at the end, what is constant for 3 to 4 seconds? The position is constant, therefore the object is not moving. Okay, so here's a little summary because now we're going into velocity versus time. Those were all position versus time graphs. Velocity or speed versus time graphs look very, very similar to the distance versus time. Except because time is still plotted on the x-axis, that did not change, but now the speed slash velocity is on the on the y-axis. So instead of our slope being velocity like it was in distance or position versus time, For velocity versus time graphs, our slope is now acceleration. And a huge thing that many kids generally get wrong is that a flat line means that something is not moving. For a position versus time graph, that is 100% correct. For a velocity versus time or a speed versus time, that is not correct. It means that that object is traveling at a constant speed that whole time. And looking at the graphs again, this is accelerating, so the speed is gradually increasing as time goes on. And this is the exact opposite. You can think of either a negative acceleration, a deceleration, accelerating in the opposite direction. It was referred to yesterday as the braking rate, any of those, but negative acceleration, deceleration. All right, and comparing a greater acceleration to a smaller acceleration, this is what the graphs would look like. So the dotted line, an object is moving faster or greater accelerated. All right, another summary. If you guys want to read through this, go ahead and pause the video before we move on. All right, so for this one, it does not have any instructions directly on the slide, but what I would like you guys to try doing is write a short story about what might be happening in this graph. So if you want to make it about yourself, about some time that you were first steadily accelerating and then you were going at a constant or steady speed, so not changing speed, then accelerating, and of course decelerating. Come up with a little story so that you can visualize what this may look like. Go ahead and pause the video. All right, so here's the story I came up with, and I added a title so that the graph made a little bit more sense. It is a distance run with Mrs. Hilt, and I decided to make the time in minutes, going up to 50. So Mrs. Hilt starts the run by accelerating for the first 10 minutes. The next 20 minutes are run at a constant, unchanging speed. Then Miss Hilt picks up the pace and accelerates for 10 minutes. Finally, Mrs. Hill begins her cool down by decelerating or having a negative acceleration for the final 10 minutes until I come to a stop. Oh, sorry. And if you guys had any questions about what your story was, if it was something that was true and actually represented by the graph, feel free to send it to me in email and I will let you know. All right, and for these last ones, what do you guys think is going on in the video? I want you to pause it and say what is going on in each, and press play to hear the answers. All right, first graph, the speed is constant. So the object is traveling, but at a constant speed, maybe 20 meters per second. Second graph, the object is decelerating or has a negative acceleration. And last one, the object is accelerating or has a positive acceleration. All right, thank you guys for watching, and please let me know if you have any questions.